Welcome to Chapter 5, the periodic table. This first section is going to review a short history of the periodic table and kind of introduce you to the modern periodic table, how to interpret it, and learn how characteristics of the elements led to a logical way of grouping the elements. So think about this. Think about going on to iTunes and everything's all mixed together. All the music's mixed together. How could you tell which ones are pop songs from the rap or the jazz or R&B? How could you figure out what song you wanted? If the songs weren't arranged in a pattern, you wouldn't know what kind of song you had chosen, correct? So a lot of thought went into how to categorize all those songs and put them into kind of folders and groupings. It's kind of like scientists in the early 1860s. They had a similar problem with the elements. At that time, in the 1860s, scientists knew some of the properties of more than 60 elements. However, no one had organized the elements according to those properties that were known. Organizing the elements according to their properties would eventually help scientists understand how those elements interacted with each other. So let's get into a little bit of history of how this uniquely shaped table kind of came about. First of all, the name Dmitri Mendeleev should stick in your head. Mendeleev was a Russian chemist, and he was the one that kind of discovered a pattern of the elements in about 1869. First, he wrote the names of the properties of the elements on cards. Then he arranged these cards, and by different properties such as density, appearance, melting point, he was able to see a pattern. He discovered a repeating pattern with those properties. And he eventually arranged those elements that they had at the time according to increasing atomic mass. He saw what's called periodicity in the table. And periodicity, or to be periodic, means happening at regular intervals, a regular repeating pattern. For instance, the days of the week are periodic. They repeat in the same order every 7 days. Similarly, Mendeleev found that the elements' properties followed a pattern that repeated every 7 elements. His table became known as the periodic table of elements. So there was a lot of pattern to it. If we look at his original periodic table, you notice that it just looked like a table. It didn't look like what we have today. Let's zoom in here to group 1. You notice that group 1, and he spells group a different way, he was Russian, has a formula underneath. It says R2O. Now, R just means you can substitute R for what element you're talking about. So if you look in this column for group 1, you see there's hydrogen, lithium, sodium, potassium. He had copper in this column, rubidium, he had silver, and some other elements. The formula on top, R2O, was how that element reacted to oxygen. So the 2 shows you that you needed 2 of that element to react to oxygen. For instance, hydrogen's in that column. He knew that you needed 2 parts hydrogen to 1 part oxygen when you made water. Also with lithium, you needed 2 lithium atoms to react to 1 oxygen atom. They all had similar formulas, and this is kind of like the periodic table that you created that was made from all of the students in your class. We noticed that elements that were in the same column reacted to oxygen the same way. If you look at group 2, you see that the formula is RO. What he noticed was all the elements in that column reacted to oxygen in a 1-to-1 ratio. In the next column, R2O3, you notice that all of those elements, like boron is the first one in that column. Boron, you needed 2 borons to every 3 oxygens in order for them to react. And that went on, and that was one of the clues that he had to arrange them into the columns. He also, if you notice, put them in order of increasing atomic mass. And remember, the mass is the protons plus the neutrons. So he placed them in order of atomic mass. Now you see, for instance, right here in group 3, that there's a blank. In group 4, there's a blank. He knew what the mass must be, but there was a blank because they didn't discover that element. So he kind of left it there, but he kind of knew what properties he was looking for. And I'll show you something on the next slide that kind of illustrates that a little bit better. But he came up with the periodic law. And the periodic law states that the properties of the elements are a periodic function of their atomic mass, meaning that their atomic mass increased in order, and a lot of the properties were very periodic. Every eighth element, you started repeating that pattern again. And you'll see what I mean as we go along. But there is a pattern to it. Every time you get to the eighth element, it kind of repeated and started over, and you ended up grouping elements together according to their properties. In this slide right here, it shows you that blank that I talked about in group 4. Group 3 and 4 had a blank, but this one's focusing on group 4, the blank at 72 for the mass. He knew that this element had to have a mass of 72. The density he assumed was going to be around 5.5, and how he came up with that is he looked at the elements that were on either side of this blank, and he said it needs to be somewhere in the middle, kind of close to where these other densities are. He knew it had to have a certain melting point based on what other elements were around that element. Also, the column kind of told us how that missing element was going to behave. And the color also kind of matched what the other elements in that column had. So the other elements in group 4 were gray in color. Later, we discovered that germanium was that element, and he was dead on with his predictions, that germanium had all the same predictions as far as properties that he predicted. As you can recall, the periodic table has those 2 rows that are on the very bottom. And I told you maybe in a chapter or 2 before that we actually have arrows that kind of tell us to go from 56 down to 57 and across that row on the bottom. And then when we get to 88, go down to 89 and across that bottom row. The lanthanide and actinide series, they're called. Well, if we were to take those 2 bottom rows and kind of shove them into the main table, it would push everything to the right-hand side and make our periodic table really, really wide. And a lot of people say, well, why didn't they just do that? Why didn't they just shove those 2 rows into the main table? Well, if they did that, it would make it very wide, and it's really kind of silly because of wall space and in different rooms and stuff. They literally couldn't get it in textbooks. It was too wide for, to place on walls. They just wanted to put them down on the bottom because a lot of those things were man-made. They weren't discovered when most of the elements in the top part of the table were discovered. So they left them underneath. But if they were to put them in, it would just make it really wide. So it's just kind of a little fun fact for you. There were a lot of gaps. When you did your periodic table with your classmates' names, you noticed that there was a couple gaps. One of the gaps you had to put smithium in and predict my properties. But there was a lot of gaps in Dmitri Mendelev's periodic table. Remember, he arranged it by atomic mass. Henry Moseley was his student in his labs, probably a PhD student. He kind of looked at what Mendelev's table looked like, and he kind of rearranged it because there was a lot of gaps, and they just weren't satisfied with that. So they rearranged it. Henry Moseley rearranged it according to atomic number. That's the number of protons in the nucleus, and it worked. A lot of the gaps were filled in. All of the properties were still in their same columns. All the trends were still working out. And it worked, and that is how our modern periodic table looks now, in order of an increasing atomic number. So the modern periodic table has the elements classified into 3 categories: metals, nonmetals, and metalloids. And they put these in those 3 categories according to their properties. Now you're also going to learn that the number of electrons are going to be very important in the outermost energy level. This is called the valence, and that's going to help us determine which category these elements are also going to belong in. The zigzag line also helps you find where the metalloids are and how the metals are located on the left-hand side of the zigzag and the nonmetals are located on the right hand of the zigzag. What are metals exactly? They're going to be shiny. This is kind of a recap. Shiny, malleable, meaning they can be pounded into sheets. ductile, meaning they can be drawn into wires, like copper is very ductile, and good conductors, meaning they can conduct thermal energy or electrical energy. Most of the elements are on the periodic table are going to be metals, about 90% of the elements on the periodic table. They're found to the left of the zigzag. They don't have a lot of valence electrons. That's going to be the outermost electrons in their orbital rings. And we're going to talk about valence more and more as we discuss bonding, but the metals are going to have 1 to 2 to 3 valence electrons. Most are going to be solids at room temp. The exception is mercury. Mercury is the only metal that is a liquid at room temp. Nonmetals are going to be often gases. They're dull, they're brittle solids, and they have low melting points, meaning that if you were going to melt a nonmetal and the metal at the same time, the nonmetal would melt first because it has a lower melting point. They're found to the right of the zigzag. They have a pretty full or completely full valence. Their valence is about 5, 6, 7, or 8 electrons. 8 would be a totally full valence. And you'd have to recall from your memory the SPD orbitals. Remember that the first orbital fills at 2. There's only 2 electrons, but the second one fills at 8, and the third one can fill at 8 as well. They also combine with other nonmetals to form diatomic molecules. Only nonmetals do this. What I mean by that is that you could get an oxygen bonding to another oxygen to get oxygen gas, and that formula would be O2. You get nitrogen and nitrogen to do N2, which is nitrogen gas. H and an H, hydrogen, hydrogen is hydrogen gas. So nonmetals like to do that. It's called a diatomic molecule, meaning 2 atoms combining together that are the same element. Down below you see carbon's a nonmetal. You see CO2 is an example of a compound that's made up of all nonmetals. Nitrogen's a nonmetal, chlorine, and oxygen. And if we go back to the metal side, I didn't talk about this before, but sodium is a metal, calcium's a metal, zinc's a metal, iron's a metal, magnesium's a metal. So just to refresh your memory, we're going to go over this in the next section as well. The metalloids are going to have characteristics of both metals and nonmetals. This is all repeat. There's going to be 7 of them located on the zigzag. This diagram down here is actually wrong. This astatine right here is not a metalloid, it's a nonmetal, but polonium, which is right next to it, is a metalloid, so these two should be flip-flopped, and we're going to actually color a periodic table in class. Some of these metalloids, this should be some are great conductors of electricity. Some of them can conduct and some do not conduct. The ones that are located on the left of the zigzag probably have more characteristics of a metal, but something's keeping them out of that category. And the elements kind of on the right-hand side of the zigzag are going to resemble nonmetals. Something's keeping them out of that nonmetal category though, so we place them in the metalloid category. Each element is identified by a chemical symbol. You already know this. And each square of the periodic table contains the atomic number, the atomic mass, the symbol. Sometimes it's the average atomic mass, so it'll be a decimal. The chemical symbol for each element usually consists of 1 or 2 letters. You know that. The first is capitalized and the second is not. Rows are called periods and columns are called groups. Thank you very much for your attention, and I look forward to seeing you in class.